Hello and welcome back or welcome to my YouTube channel. My name is Shaheen and I work on the posting side of LLMs, and currently I'm not associated with any company and I am building independently. If you can maybe collaborate with me, you can connect with me on my LinkedIn. And today in this video we will talk about evaluation of a large language model. So we will be taking a model from Hugging Face, maybe Qwen3 0.6 billion parameter model. This is the smallest version I found there, and I have my own architecture ready here, coded in pure PyTorch, and we'll be downloading weights from Hugging Face, and then we will dump those weights into our own architecture, and then I will show you how we can run the inference on this open weight model. And then we will be experimenting with two models. First we will be taking a base model and then reasoning model. We'll be only downloading one variant of the model, and then I will show you how we can make a base model or reasoning model by just adjusting those thinking tags in the assistant generation. And without further going deep inside this, I will show you one of the person that I'm literally inspired by. This is the Sebastian Raschka, and he got this amazing book of his. This is reasoning from scratch. Actually, if you want to understand how these frontier reasoning models are built from scratch, you can directly and choose this notebook, and he got this lot of implementation of his own book here. And this is open source actually. If you can go and maybe go deep inside any one of the notebook, you can see the depth he has literally covered. And in this video we will talk about this evaluating reasoning models. I haven't copy pasted an entire notebook there, but I have made sure I will explain these things in small and easy to understandable easy to understandable terms, actually extra. So if you want to understand how large language models are built, I recommend you to go to my course. I will put the link in the description so you don't have to worry about this. You go to the Qwen3 in the base model folder, and you can see how this Qwen architecture is actually implemented from scratch. And I have other details here. I have properly wrote the comments, like the shape is what goes in and what comes out actually. So if you want to go deep inside this, you can learn a lot of things by just looking at the notebook or maybe implementing in your own way. And today we will be evaluating reasoning models from scratch. So in this video I will take this model, and that is the Qwen model, and then we will be running inference on it. Okay, this is the architecture, and you can see this architecture. It uses group query attention, it uses rope, it uses RMS norm, it uses CLU activation, and then you got 151k vocabulary size, and it is mostly similar to Llama 3.21 billion parameter model. And without wasting any more time, let's get down to work actually. So first we will be downloading a model from Hugging Face, and we have our own architecture ready. Then we will be copying those weights, compare the layers, and then copy the weights of the the respective layers, and then we will load that model into our system. And inside this I'm using the Lightning AI. If you don't have a high-end GPU personally, you can go and use this Lightning AI Studio. You can get some free credits there, and there is this a lot of GPUs are available there, like the Tesla 4 GPU that also the Google Colab also provides to you. And yeah, so we'll be downloading model from the Hugging Face, tokenizer extra. And then okay, so first, what is the difference between the base model and the reasoning model here? So actually the base model is actually fine-tuned on the instruction tuning, the instruction tuned data sets, extra instruction based data sets. So maybe I'm interacting with the ChatGPT right now, and I ask you what's the capital of France, it will give me the capital of France is maybe the Paris, and how it knows that the user is asking me something. So maybe this is how we tell the model that we are giving it the query and you have to respond to us between these user and assistant tags. So actually I'm based in Kashmir and it is raining heavily. Okay, and now let's talk about the Qwen3 model that we are going to use, Qwen3 0.6 billion parameter model. Okay, so this is the smaller model, and it can literally fit your GPU, the small GPU if you have. And yeah, so how we can make this model a reasoning model is just by adjusting the tokenizer. Yeah, by just fine-tuning a tokenizer a little bit, we can make a base model a reasoning model. How? By just implementing these thinking tags in the assistant generation. The generation that the model will be generating, the response that the model will be generating. So we are not only telling the model to generate the response, but we are asking it to think inside these thinking tags. If you ask any math problem like 3 plus 2 plus 3 plus 5 divided by 12, it will go step by step, reason step by step, and you can see there's reasoning traces like in the ChatGPT or maybe the Gemini or the Grok, etc. And this is how these reasoning models are built from scratch, maybe at these frontier labs. So it will take a problem, it will break it into small steps, and then it will go deep, maybe apply some formulas, equations, and then it will give you the answer in the end. Yeah, so how we are making this base model a reasoning model? By just adding these thinking tags in the assistant tags. Okay, so this is how we tell the model that you have to go deep and think longer by allocating more compute at inference, and you can think longer, you can break this problem into smaller chunks, and maybe later come up with an exact solution. Yeah, that's how we're going to evaluate the models. Okay, so tokenizer of Qwen, I will show you the tokenizer of Qwen, and then we will move forward actually. So if you go to the Qwen.5, you can see the tokenizer here, Qwen3 tokenizer. Okay, this is the tokenizer, and these are the parameters that are responsible for us at thinking. And if we add this, if we tune this self.add thinking equals true, later on I will show you how it is done in the notebook when we are going to literally generate a response from a model. And if we do self.add thinking equals true, it means we are telling the model that you have to add the thinking tags in your generation. Okay, and when you are adding the thinking tags in your generation, it means you have to go deep inside the problem that the user is posing to you, maybe a math question, maybe a coding question, or maybe any type of math problem, etc., that needs reasoning, maybe a step-by-step solution. And that's how we are going to evaluate and how we are going to approach our problem today, that is evaluating a reasoning model. And if you have another details here, let me explain that, or if no. Okay, first let me talk a little bit about the pre-training side. So actually what happens in the pre-training, we train a model on some random text without any guiding the model how you can generate text. And so it's like the autoregressive fashion of LLM is just like you are getting the whole encyclopedia, Wikipedia, or all of the internet data there, and maybe the semi-supervised data, semi-supervised data, maybe I can see it's not properly cleaned, or maybe it is semi-cleaned extra. So you are at least giving everything to the model and asking the model to predict the next word. So actually in the pre-training side, the model is only capable of generating the text, the next token. But later on, when we are going to make that base model model that we are literally going to ship to the users, like the ChatGPT, so you need instruction fine-tuning. And when you are doing the instruction fine-tuning, you are asking model how to behave in real world, like how to respond to user queries. And then if you want some more improvements in your base model, and that comes under the post-training side that we are talking about right here. And when you want your model to actually answer your math problems or the coding questions, so it means you have to train it on the reasoning type of data. Okay, and by training on the reasoning type of data, it means that you have to teach your model how to respond when you see any math problem, and how actually that I have to now go deep step by step and then come up with a solution. Okay, so that's how these reasoning models later on work. Actually, these are the base models, they are instruction tuned models, and they are later on trained on some reasoning data. Okay, and by training on the reasoning data, it means you are literally training model to actually see these thinking tags and go deep into the problem and answer the particular query. Okay, so today in this video I will talk about the base model and I will talk about the reasoning model. That's why I'm showing to you how the base model works. It takes user query and it gives the response, so it's not going deep inside any kind of problem. But if we talk about a reasoning model, it means the assistant is actually adding more tags. These are the think tags inside the assistant response. So when we ask any type of query, maybe a math problem, it goes deep step by step, apply formula, apply equation, and then come up with a exact solution. At least most of the times, depends on the model, how the model is trained. Okay, so without wasting any more time, let's go into our notebook. So I'm not literally going to write every line of code here, but I'm going to run these cells because this is a pretty big notebook, so I'm not literally going deep inside everything right now. Maybe I will come up with a video later on that will exactly show how we can do this and that. I mean the exact number of functions here, maybe that will exceed 100. I mean you can't like say how many functions I require. This is a architecture heavy notebook, and I have a lot of things that I'm implementing, I mean importing from the Qwen3. I will share the notebook with you in the description box, so don't worry about it. Okay, so first I will be running this notebook. So what is running this cell? So what this will do, it will download the model from the Hugging Face. So actually we are downloading the model from Hugging Face. Okay, it's already downloaded in my root directory. You can see the Qwen, and this is the function that is responsible for downloading the model. So it is actually using the Hugging Face app, and there is this function called snapshot download. Okay, so you can go deep, it's not a big deal. You can later on read this notebook. I will give the link of this notebook in the description, so don't worry about it. So here I have my own, I told you I have my own architecture ready, and I have the configs actually defined there. Actually I took it from Sebastian's notebook, and I don't want to write it from scratch anymore because it's already there, and I want to break this thing in more simpler terms actually. So I have a little bit, I mean fine-tuned the tokenizer in my way, and that was working for me. And you can go deep inside the tokenizer also, that's also available here that I showed to you. This is the tokenizer, these are the special tokens, and there's a lot of things that happen, like how we encode things, how we decode things, and later on this is the how we, I mean, wrap the chat. If I'm going to explain this, it will take a lot of time. This is the function that is literally capable of making your, I mean your model, the reasoning model. Okay, let me close and let me run this cell. So we have a lot of things, but here I want to focus you on, I want you to focus on this thing. This is the function that will return as the model and tokenizer later. So actually we are loading the model and the tokenizer here, but we have this parameter that is which model, and if I am going to pass base into this parameter, it means we are going to use the base model. So we are not going to, I mean, add these thinking tags to the assistant response, these thinking tags to the assistant response. It means we are only going to add the assistant tags and asking model to generate a response. That's it, simple. And but if our which model equals reasoning, it means we are going to add thinking, and we are going to add thinking tags in the assistant generation. Okay, I mean the prompt generation, I mean the response generation of that the model will generate etc. These might be true with the base model also, but this is a catch. This is only true when you want a model to reason on a particular problem, so you add these thinking tags in the assistant tags. Okay, so I think it is clear now. So this is, we are taking the model.shape tensors from Hugging Face that we download, and we have our own architecture. We are passing the config, and then we are loading the weights. So this is the function that is exactly here in the Qwen.py. Okay, load HF weights into Qwen architecture. Well, this is the function responsible. It will compare every layer there, the weights associated with every layer, and then it will copy those weights into our own architecture. So this is the function that is responsible for it. You can ask ChatGPT, go deep inside it and explain the things extra. Okay, and then we are passing the params, and I mean params equals weights that we have downloaded here, and then device equals the CUDA if there is CUDA, and if not then it's CPU, but we have Tesla for GPU. So we're using a free notebook here from Lightning AI. Thanks to Lightning AI. It's not a sponsored project. It's like, come on, this is my first video, and this will be returning a model and tokenizer. Okay, we are not using the toys.compile. This is, so what this toys.compile does, it makes your model, I mean the inference little more faster, but it internally uses a GID compiler. So I'm not going deep inside. Maybe we'll come up with a video later on, but we will run this cell right now. Okay, it is loading the weight. Okay, it's done, and now I'm assigning which model equals base. I'm using the base model, and I'm calling this function. It will give me the model and tokenizer. Actually, everything I am running here is running on this virtual machine here on Lightning AI. Actually, if you can see SSH into Lightning AI Studio. I'm using this weatherboard powering extra whatever the protocols are there. I mean, I have my connection set up with this local. I mean, I'm using the local VS Code, but it's connected with this Lightning AI Studio. You can use the same by using the SSH. Oopsie, wait. You can use this connect with SSH here, and you can copy paste some of the commands there, and you can use this feature also, and it will look like your own local VS Code. Okay, now we are going to use the KV cache. Actually, if you know about the KV cache, like if I have the prompt like what is the capital of France, so I'm passing it into the model. So later on, what the KV cache does, KV cache will take this whole sentence like what is the capital of France, and instead of recomputing that KV projections again and again, we will compute it for the first time, and then we will be reusing it whenever we need. Like the model generated the capital of France is Paris, so when the model is generating the the, and it means we are not recomputing those KV projections for the previous tokens. Instead of recomputing, we are saving them or we are caching them, and then when the model will generate the first word, the first token, and then the will be added to those previous tokens also, and we will be having these KV projections of all these previous tokens to predict the next word. And similarly, when we will be predicting the capital, and when we'll be predicting the capital will also be cached later on, and then the capital of the France is Paris, etc. So this is how we use the KV cache. Okay, so I hope you got the intuition, and yeah, so it saves us a lot of memory, and later on, and sometimes this KV cache can go even bigger and bigger, and then it can become a memory bottleneck, and there are this inference engine like the SGLang, LLM, etc. that can work pretty fine, or maybe there are a lot of optimizer techniques there. So I'm not going deep inside that. So let's begin our work, and we'll define our first function, that is generate text string with KV cache. So this is our inference function. We are inside the inference mode, and this is our tokenizer. Tokenizer will take the prompt and it will unsqueeze it. It will add the badge dimension. If you don't understand it, take this line and paste it into the ChatGPT and ask chat to explain things. And this is how you learn in the modern way. Okay, modern world actually. And then I'm setting the model to eval mode actually, and then I'm calling this KV cache function, and inside this KV cache function it takes one parameter, that is the N layers, and we are giving it the N layers from the model.config that I showed to you. I think if you go inside this Qwen3, you will see these are the configurations that the Qwen 0.6 billion parameter model takes, and I am passing it, and then I am running one of the initial forward process that will literally, and first I am setting the model reset KV cache, so it will be calculating the KV cache or storing the KV cache from scratch. And here what this does, it will first, I may run the entire prompt into the whole layer. Let me show you the full architecture. It will go from here, and then you will get the output, and then it will save all these tokens inside this, and then it will take the last token, and then from this last token we will do the argmax. So what does mean actually? Suppose, let me go to the, let's be confused where I have to go. Okay, this is the whiteboard here. Suppose I have 5 tokens here inside of one batch, and this is 4th and this 5th one. This 5th one will give me the next token actually. This will be responsible for giving me the next token. Yeah. So if I have the 151k vocabulary size, I will have 151k etc. the logit scores, and let's suppose this is one that is responsible for giving me the next token. Maybe this is the index 50,025, and this has the largest logit score, and we will take this token and decode it later on. So this will be our next token. Okay, let me get back to our stuff here. Okay. This is, so what this means, it means we are taking the last token from the whole sequence length, and from that whole sequence length we are then doing the argmax. So what the argmax does actually, it will take the highest logit score and from dimension equals -1 means the sequence length, the token dimension, and we are keeping the keep dimension equals true, so we are not going to lose the dimension, because when you do any type of operation like the argmax or the mean operation or on top of a sequence length, I mean the token sequence length, then you might lose the dimension. It means keep dimension true, it means you have your initial dimension there, so I'm not going to lose this, and this will give the new token. So we are looping inside this max new token. What this max new token is, this means we are telling the model how long you can generate on a particular query. So it means we are telling the model, like if I later on pass max new tokens equals 100 words, it means we are telling the model you can generate text only under 100 words, because sometimes the model doesn't encounter the EOS token ID. I will tell you about talk about the EOS token ID, what it is. Actually, this is the end of sequence ID, and sometimes model does not encounter that. It just randomly goes and generates some garbage, and it may maybe exhaust your compute limit at the compute power. So let's talk about this EOS token ID, what this is. And I have literally got into the problem of EOS token ID, and I have later on figured here a solution. I have got the solution later on how we can stop this, because here the function wasn't literally stopping. The generator was yielding next token, and it was literally hard. So actually my computer is a little bit heating up. I don't know why. I'm not running the model on this CPU at start. Okay, so let's ignore the warnings. Okay, now let's talk about the next EOS token ID. If I go here, like I have literally explained the EOS token ID somewhere. Okay, this is it. So let's suppose the model is generating a response. First I have what is the capital of France, and then it is generating a response. The capital of France is maybe the Paris, and then how the model knows, actually it has to stop somewhere, and that's the power of EOS token ID. And how we actually tell the model, train the model on these things. So we actually, when we are doing the instruction fine tune, we embed this token IDs there. The token is there, like these tags there, like user assistant EOS tag and the thing tag, and it is that the model is learning like when to behave in a certain way and when to stop generation. And EOS token ID, end of sequence token ID, is responsible for telling the model that you have now completed your response and you have to stop. Okay, I hope this is clear now, and this is how we are taking the argmax function. And then I am saying that if I have got some value here, the EOS token ID will be given by the tokenizer later on. I will show you how it is done. And if we got, and then we will compare the next token with the EOS token ID. If the next token equals the EOS token ID, it means we have to break the generation. Otherwise, the generator concept will. I hope you know about the ALD keyword. The generator concept in Python. Actually, it computes things, it stores it in the memory, and then it gives back to you. So it's not like it will take all the previous token and save it into the memory or compute it. But it is doing this stuff. Its job one by one. That's how the LLMs are generating text, like the ChatGPT is generating text token by token. Yeah. And then I have the wrapper function, the text generation wrapper function. It's calling the generate text with KV cache function, this function, and we will be taking this token that will be given by this yield keyword, and we will take this token and print it here. First we will decode it, and then we will be printing it. Okay, and main is on the same line, and flush equals true means we are streaming like one by one. Okay, I think that's the meaning of flush. Yeah, but first we are squeezing it. We are removing the batch dimension that we added here. Okay, I think it's clear now. So let's now go and call the text generation function, and I am passing max new token is equals 600. It means our limit is if the model is going to generate the text, it has only the 600 words to generate the text. Otherwise, at 600 word, at the 600th token, it will stop generation if it still didn't encounter this EOS token ID. Okay. And here I'm going to say, talk about 5 things here. EOS token ID the prompt. Okay, so now we have to pass the device, and If you have Coda or if you have CPU, the torch.coda function will automatically do this for you. And inside the prompt, let's say closely, like this is the raw string. I mean, I am passing one of the math functions here, and I will ask model to generate text on this. So I will generate, I mean, run this again in front of you. Before that, let me run this function. Okay. Or you can see how the model is generating the text. So it is running on the Tesla 4 GPU that is provided by the Lightning AI. Okay, you can see the generation. There is the problem. See, as I told you, the model is still not capable of stopping because it has generated the same answer, the final same answer again and again. So, do you see this like this lousy output from a model, like the garbage output? Maybe, yeah. So this is the pre-processing stuff that we have to go through to later on evaluate the model, because this is the main problem and this is the painful problem to like clean this data and make it usable. So if I take this portion, this is the final answer actually, and if I pass it to the ipython.dispipe, I'm importing the math and then I'm displaying it. I'm passing this in the raw string. You can see what this means. This means 14 divided by 3, and that's what this all the text here means. Okay, so this is a little bit complex to understand, and that's why we have to go through a lot of data cleaning here, the normalization, the latex fixes, etc. So I'm not going deep inside everything. So now let's talk about this one. So I will try always, I mean, to go fast here actually, so we can go into the evaluation mode and see how we can evaluate model and how our model will actually perform on the base model and the evaluation model. That is the sole purpose here actually of this video. But I can promise you, like in the next few videos, maybe if I got time, I will definitely, I mean, try to go deep inside the latex fixes and the functions that I'm going to show you right now. Okay, so first there is this wrapper function. What this does, this function is actually giving us this answer. So this will be the only answer that we are going to deal with, because this will be, I mean, responsible for later on when we'll be running the evaluation mode, that the model, this is the generator response from the model, and then we'll be comparing it with the ground truth. Then we will see like the difference. If the model got it correct, then we can, I mean, see like the preceding model or the base model is performing good. I mean, that's that we will say like this is a thing that we have to actually deal with. So this is the only thing from the entire generation, and this will help us to later on determine if the model is literally giving us the correct answer. Okay, and this will help us in evaluation. So this function is giving us only this much, and if this much is present in the generation of the model generation, the response generated by model, so it will give us the true, else it will give us false. So this is the same text generation function. And here we got some other things. As I told you, the model was generating the same answer a lot of times, and we got to fix it. And this was the problem, and I got to fix it. You can see this function is responsible for stopping it. Otherwise, the logic will go here. Okay. It means inside the tokenizer, we are asking tokenizer if we have, I mean, the lot of stop token IDs. So what actually happens? There are a lot of chat templates in the market. Like, I will show you this example. I asked Gemini to give me some of the examples. Okay, some of the models are, I mean, implementing IM tag at the end instead of the ending tag, or the EOS token ID, end of sequence token ID, and some are using the IM end, or some are using the, maybe this is an instruction, some are using EOT ID, and some are using IM end again. This is a Qwen model, alpaca. Okay, this is llama format. Llama format is using EOT ID at the end, or end header ID. Okay, end header ID. This is start header ID and end header ID. So I'm assuming this is end of sequence. Okay, EOT ID. Okay, this is starting from here and this is ending from here. This is ending here. The capital of France is Paris. So this is the word responsible for stopping the model from generation anymore. Okay, and here you got I am end. What is capital of France? I am end. Okay, I am start assistant. Okay, the capital of France is Paris. So you can now see that many type of models like the llama model, there's a difference between the chat template. Like some models are using the EOS token ID, some are using IMAD, some are using EOT ID, etc. So it's literally hard for us to see which model is literally responsible for stopping the generation. Otherwise the model will generate the response like this, see, and it will sometimes go even beyond if we don't have any token limit. And this is responsible for the token limit, and that is this function here, max new token. And if you are going to give it to the 2000 words here, passing the 2000 words instead of 600 words. Actually lost. Okay, max new tokens. And if you are going to increase this number to 2000, the model will continue generating the text and it will never encounter the EOS token ID. So we have to fix this. So actually I am asking tokenizer if you have some other token IDs inside your vocabulary, and if the model got some stop tokens there, more token IDs than the EOS token ID individually, so it will give me those token IDs, and we will be storing that inside this. And then I'm saying if not token IDs, if there are no token IDs inside this token ID, stop token IDs, and then we will use the default tokenizer.eos token ID. But this is actually there, I will show you where this is. But if there are stop token IDs, then we'll be looping inside those for token ID into stop token ID, and we'll be taking that token ID, and that will be using later on. We'll be passing that into the KVK generation function here. And if still there is no token ID there, and we have to deal with this, and model is not stopping, so what we are going to do? We have the function, we are passing something stop after boxer. What this stop after boxer is? This is this function. If there is a box inside our generation, if we got this, it means we have got the answer. And if we got the answer, then there is no need to go beyond and generate the same text again and again. So that is what this is doing. If stop afterwards after boxer equals true, that means if this condition is true and has completely got true, it means this function gave us the true result. Return a true, it means it will stop generating the text anymore. And if stop text is there, it means stop text is question or answer. It means let's see what this is. You can see here final answer, or maybe the model is generating the same question and answer again and again, like this. Maybe it will generate the whole set of answers again and again. Or if it encounters the final text, I think this means is the same. And if your model encountered the question and answer again, it means you have to stop generating text. So there is this condition. And any stop text and stop text, it means if you encounter these two things in your response, again it means you have to stop. In the generated text, the generated text generated by the model right now. And if you encountered any question or answer, or if you got true from this function, has complete boxed answer, and stop after boxed equal to true, it means you have to stop generation. Because here there was a problem with us where we were generating the same answer, the model was generating the same answer multiple times. So we have to fix this, and we got these things to fix it. These things. And we got these 3 lines of code. Yeah. And now I will show you how it is working. And let me run it again. We had the problem because the model was generating the same answer multiple times, and this time we got a fix. I have actually tested this all. Okay, we got the answer, and you can see for the single time the model has now encountered that the boxed answer has already been generated, so we're not going to generate this anymore. So we have fixed our problem. And then I will show you one more step, how we can convert this lousy and the garbage text here into pure math. So we will be calling the ipython.display import latex. We will compare the latex function, and then we will display that, and we will pass this generated text here to the latex function from ipython.display. Okay, and then you can see the clean version of this, like how the ChatGPT shows you the on the UI. Maybe you're asking ChatGPT a problem and then it will show you how it looks actually, in the plain English, or maybe the plain printed text, etc. And you can see how clean this is. And now I will tell you one thing. We have to only deal with this final answer, 14 divided by 3, this box. Yeah, and this is the only thing that will be responsible for our evaluation. Okay, so now I'm not literally going deep inside. I will give you the overview of the functions that are after this, that are taking this garbage text and making it a clean and giving us the clean output, that is 14 divided by 3. And these are the functions. Actually, this is just I was expecting, I wanted to test the cat.rfind function that we used here. Here we use the text.rfind function. It will give the index where this text starts that you are passing it. And then we got the get last box function. It's doing some type of work. Maybe it's giving you the, if there is a boxed. Okay, so it will give the last boxed answer. Like if your generation has some, the garbage text, but it will look for the last boxed answer, this answer, and if there is answer, it will return that answer to you. I'm not going deep inside this function. You can go and maybe look at them. So this will extract the final candidate. So what this function will actually does, if you're passing this function, this boxed answer actually, and then it will, if you're passing a whole set of, a sequence to it, it will extract this boxed answer, not the boxed answer, but whatever is inside that boxed answer. I think it is extracting whatever is inside that boxed answer. Okay, yeah. So if there was no box or nothing inside the box, maybe there is a number, then it will return the number. Otherwise, if there is a plain text, it will return the plain text. So you can read this function again. I'm not going deep inside this, because it will literally take the memory of my brain power. And then you got this latex with, this is one of the complex functions here, and it got a lot of latex syntax here. So it's literally complex to understand. Maybe I will get a new video on this, how we can work with the latex syntax, etc. So I'm literally weak inside in this field right now. I have never worked with the latex, so maybe I have to go a little bit deep and later on come up with a video. So this is actually normalizing the text. It is like, it's actually cleaning the data. Like you got this garbage type of data here, yeah, and it is cleaning it up and doing some type of normalization. And you can go deep, maybe ask ChatGPT to explain this, because this is so much complex. So you can see the the comments here. This is remember degree notation, and this is the latex syntax, how we actually match. If there is a match inside the text generation by the model, then it will remove that. Okay, and there are a lot of them. I'm not going deep inside this, will literally take my mind. It's literally hard to understand this thing. Okay, maybe I will ask ChatGPT later on to teach me the latex, etc. Yeah. So this is normalizing the text. It means if you are passing this garbage text, then it will give the plain output in these brackets, in these parentheses. And then there is the simpy parser. What the simpy parser does actually, okay. Simpy parser gives you, like if you're passing any type of math function here, it will give you the response inside. It understands the mathematical symbols like we humans do actually. So like if I'm passing 2 into x, or 2 cross x plus 3 cross x, it will give the 5x. It means it's just understanding the math like how we humans do. Okay, so nothing big. You can go deep inside this function or maybe ask ChatGPT to explain. Then there is the equality check. If there is a match, like mathematically, like 14 divided by 3, you are passing it this way, or the 14 divided by 4 point and 13 divided by 4. It means these are same actually, or it will give you the true if these conditions are true. If there is a match, like for example, okay, this is the example you can explain, understand this. If there is 0.5 equals to 1 divided by 2. Yeah. So as humans, we can see this, but how we can, I mean, teach the machines this number is exactly equal to this. So that means that's the power of the equality function, equality check here. You can go, it is using the simple parsers to, I mean, understand the mathematical symbols, etc. So you can go inside it and maybe explain. Maybe I will come with a video later on, but not this time. I'm going literally hard at the evaluation. Yeah. Okay, now there's the grading function where the grading answer does actually split into parts. Okay. So there are a lot of functions. I'm not going inside this. You can maybe later on go. This is just the pre-processing of the text. It makes your test. This is the demo file we were expecting. I mean, we have actually tested with these things. There, I got these things from the Sebastian's notebook, and you can see it passed all the. Actually, it is verifying if this syntax, if this is same as this, and this is the normal 3x4 and this is the latex, and then maybe this is a simple raw string, and it got frag brace 3 brace 4, and that equals to 3,4 3 divided by 4 when we, I mean, normalize it. So here comes our main work. We are loading the data set. Okay, but I have to run this, I mean, run this code cells also. Okay. Okay, we will be loading. You can see how it looks like. So we have to take the simple first problem from here. This is the chat template. This is the prompt. This is the math problem we are testing it on. And then the model will generate this response. That is 2, and this is not the correct response it is generating. There are multiple, I mean, prompt templates here also. And this is the mini eval demo. Let's run this. Okay, this is the answer it gave to you. This is the function responsible for giving you the progress. Okay, so let's talk about the progress function actually. So this will show you the timer, I mean the estimated time remaining extra, and it will show you the the display, visual display, like how much is processed already and how much is left extra. That visual that gives you like the feeling that something is happening in the, and like something is happening under the hood, extra. So this is the main evaluation function. You can go deep inside this function also. There is this code and I will provide the link in the description, extra. So I guess we should talk about the evaluation function mostly. So here we are passing it the math data that we already downloaded from Hugging Face. Yeah, this is the function. Here is the data. So we will only be passing maybe 10 problems right now, because we are not going to, I mean, wait for 500 problems. So maybe we will test it with 10 problems on the base model and the reasoning model. Yeah, so this is the evaluation math problem, I mean evaluation function. You can see this where we will be saving the checkpoints in our dictionary, and we will be getting dictionary like this. Oopsie. Yeah. Like this, like the index, the problem, and the ground truth, and all these things. You can see this, I mean the generated text. And the generated text contains the thinking tags, the think tags that I talked about few minutes ago actually. So yeah, this is the function. It will show you some real matrix. There's not a big deal. You can go into the code, etc. So yeah. So maybe I should execute this function. I mean, execute this function as I already did, and now we'll be executing this function also. And which model will be in the base model already that we assigned it, because we are not going to use the reasoning model right now. We will test it on the 10 problem sets. Okay. Yeah. Okay, so I am running the loop, and we'll wait for 5 minutes. Maybe I have already ran it one time and it gave me the performance. If I show you here, so by running the evaluation of the first 10 problems, the base model got one problem correct. Actually, the result is that were being here displayed here. So that got only one problem correct, and with the accuracy of 10%. Okay, out of 10 problems, only one problem was correct. And then I ran the reasoning model actually. And when I ran the reasoning model, it means we have to like assign this which model equals reasoning. We have to set the reasoning which model equals reasoning, then load the model and tokenizer with this which model parameter. And then I printed the reasoning model, and then what I did, I again ran this, executed this evaluation function, evaluation math 500 on the 10 problems, and then I was seeing some good results actually. So I got 60% accuracy. Out of 10 problems, we got 6 problems correct, and it took us the time of at least 7.8 minutes, okay, on the reasoning model. But on the base model, it took only 5 minutes. So I think I have literally I wrote everything here. We are now capable of improving model by maybe 50% by using those the think tags inside the reasoning model. By making that base model a reasoning model by adding those think tags in the assistant tags. Like the model is literally breaking that complex problem into these mini steps and getting us to the correct solution at least maybe 60% of times. And now the base model took 5 minutes and on 10 problems with 10% accuracy, and the reasoning model took 7.8 minutes on 10 problems with 60% accuracy. So I hope you got the intuition what we are actually doing. So I'm not waiting for this. Actually, I executed the whole notebook before I made the made this video. So I thought this will be easy. And regarding those the latex fixes and the text pre-processing, maybe I will make a video later on that, because it will be so much complex. Explain that latex and syntax, etc. So maybe I will come up with a video later on and we'll see. So I will give you the link of this notebook in the description, and you can maybe run your own applications, etc. Okay, so I think this is all for this video, and I will meet you in the next video, I guess. Okay, so thanks for having me here, and have a great life.